Okay, so I'm going to tell you this story, and please stop me because it is a bit exotic. It would be strange that somebody is an expert on everything. It's the story of time reparametrization in invariance. Time reparametrization, think of an old cinema projector. The film is given to you, but you can change the speed and non-linearly change the speed at which you are projecting your film. So you can hurry up and then slow down, etc. The film is always the same. That would be a time reparametrization. So 3 episodes. In glasses, so let me start with the simplest glass model. This model is just random couplings, fully connected. These are normal commuting numbers. We will need to keep them bounded, so we will keep them on a sphere, one single sphere. And we will study, for example, the dynamics using a simple Langevin equation. This is the harmonic oscillator of glasses. This is the simplest of the simplest glass you can make. And this is why we tend to use these models for most things. So just en passant, this model it works and has, if you want, the same kind of properties as more interesting models, like, for example, graph coloring, K-SAT, et cetera, an enormous family of models that, but if you learn how to do the P-spin one I showed you, you've learned a lot of what you need to learn. So we are going to talk about the dynamics. We start from some configuration, and in this landscape, I didn't tell you, but this landscape is on the sphere of n dimensions. It is very rugged. It has many minima, saddles. It's a very nasty landscape, as you would expect from a glass. So you launch from a random configuration your system, and the order parameters that are interesting is obviously the correlation at 2 times of the position, which tells you how you're moving. The correlation between the position and the noise, which is the response function, and the correlation of the noise with the noise, which is simply another correlation. So these are 3 parameters. There is no space, there is only time. And okay, so you try to see how this works, and you discover that the relaxation of this system has a fast time, a first time, and then there is a decay that is extremely slow. So in terms of 2 times, the small time differences, meaning high frequencies, have a fast relaxation, but then there is a kind of evolution of the system that is extremely slow. Exactly, yes, okay. The noise was white, but if you impose something at arrival, then you're correlating because you are, constraining the noise. So, ways in which this dynamics, when I said slow, what do I mean by slow? And in terms of what is it slow? Okay, the most famous case in which if you have a plastic ruler with you, you will be seeing this thing, is aging. So you prepare your polymer melt, you produce your ruler, you put it at 20 degrees, and then a month, a year, 10 years pass. And when you look at the dynamics of the polymers involved, there is a fast part where you have the vibrations, etc., which is almost as in equilibrium. But then there is a slow part where, in terms of the time difference, the relaxation becomes slower and slower as the system becomes older. So, for example, if you take your ruler and you pull from it, you will get a quick part, a quick stretching, and then a creep motion that is very slow. This creep motion is at 1 day, 10 times faster than at 10 days, 10 times faster than at 100 days, and so on and so forth. So it keeps on changing. So this is the slow part of the relaxation. You get slower as you get older. Another way of doing it is to weakly drive the system. So the same ruler that it's getting old, if you grab it with your hands and you do this to it, you're shearing it, becomes younger, and the rhythm at which you do it is going to decide how slow the dynamics of the polymers are inside. So it's another way of making slow dynamics, but this time it's not by letting time pass, but by keeping it at a constant old age just by doing something. And another way, which is perhaps the easiest to understand, is to, when you have a disordered system like the one we did at the beginning with a p-spin interaction, you change the coupling slowly. So imagine your system is trying to optimize, and it's very, very slow in doing it. But if your parameters change, then you keep on changing the problem all the time. So the system is all the time trying to catch up, and hence the parameter that decides at which speed is the relaxation is precisely the rate at which you are changing the couplings, because it's the rate at which you are changing the problem for it. And we will assume that T prime, the age of the system in the case of aging, tau, the parameter, this parameter I'm describing, are big. So the dynamics is slow, but it has different ways of being slow. So the nice thing about this model is that the dynamics is solvable, which means that in terms of the order parameters I defined before, now they are unreadable, but you know what they are, the ones I did before, and by defining these 2x2 matrices, you have this beautiful equation of motion, which is in reality not very beautiful. It's for one parameter, it is exact in the thermodynamic limit. So if I can solve it, I can put it in the computer, and it's a perfectly well-defined equation, but it is quite nasty because you see you need to remember previous times, and you have convolutions, and it's very nonlinear, so no hope of solving it analytically completely. But this equation can be solved, and even its asymptotics can be derived. And now we come to the solution, and the solution, you can check it by just putting it in the computer, has a fast part and a slow part. And now comes the point that is crucial in all this story. You had this equation of motion, and it has a slow part. Now, these terms, including a time derivative, when something is very slow, they are negligible. So the next step, and this happened, I don't know, 40 years ago, is to neglect this term for the slow evolution. So let me recap. You have the exact equation of motions. You discover a posteriori that it has a slow relaxation, and then for the slow relaxation, you decide to throw a term that goes to 0 because it contains a time derivative. And what happens, and this is the miracle that's at the center of this seminar, is that something awful happens. The moment you throw away this term, which is a very good approximation, your system acquires a time reparametrization invariance, meaning that the correlation at those two times, the function h is the function that stretches the time as you wish. You can accelerate, decelerate, etc. And you can deform time the way you like, and all of these are solutions of this equation once you threw out that. So throwing it out wasn't an innocent thing, okay? This is going to be our crucial technical point. It's actually the only technical point. So, but the reality, as I told you, is that you can put these equations in a computer and get the exact solution, and there is no ambiguity at all. But when I do a very good approximation, I get that there is an ambiguity. And so you are in a situation where you have a quasi-symmetry. This is, of course, only a metaphor. you have directions in which you can make changes that do very little, but still there is a choice of the solution, like in this case, and it's almost like a symmetry. Is this more or less clear? Okay, so now, exactly, angles are almost for free, radii are very expensive, but the angles are not quite a symmetry, they're almost. This is just a metaphor for reparametrizations are almost for free, and then everything else is expensive. Okay, so when this happened, we were all very confused. This is many, many years ago. In fact, the people who discovered this is Sompolinski and Zibelius, I believe, in '82. And then when we were working on the dynamics of aging, for us, it was a nuisance, basically. We couldn't decide which reparametrization was good. And then we did the following. You can plot the response against the correlation. So we remember this one is the correlation between noise and position against correlation. Now, you're out of equilibrium if you're doing aging. And normally you should get this -1/t, which is the fluctuation dissipation theorem. If you were in equilibrium, you should get just this straight line, which relates correlation and response. But you're not in equilibrium, and in fact, you happen to get this curve. If you plot parametrically with these times, you get this curve. I'm not explaining now why, but the fact is, it's no big deal because you're out of equilibrium, so there's no reason why you should get fluctuation dissipation. Very good. You do this in the case of aging. And then you discover something that is quite amazing. You remember these three ways of making aging I presented to you. So, for example, you can do aging, or you can do slow dynamics by changing the couplings. The dynamics changes completely because the time scales change, everything changes. And now you do this plot and you discover that, lo and behold, you get exactly the same curve. So you have different slow dynamics because in one case you decided to drive the system, in another case you decided to change the couplings, and everything changes, the speed at which the system moves changes and so on, but still when you plot this against this, you get this same universal curve. And so this at the beginning was an enormous surprise, but then one should think, why were we surprised? After all, we have just said that these degrees of freedom, which are the reparametrization, are almost for free. So whatever you do to the system, you can dramatically change the speed at which you're passing the film with very little changes, but then there will be some things that are invariant. It's exactly analog to here. If I have a system that has a quasi-symmetry and I kick it even a little bit, it will move up to here. And that's perfectly natural because I have a quasi-symmetry. It's not for free, but it's very cheap. However, climbing the hill is just it's completely another question. This I cannot do for cheaply. And then to check these ideas, one can do plots of correlations against correlations. So these are plots where the time has been factored out. And again, you see that whatever the precise dynamics, the result always is along this line. And then these people here studied the fluctuations of a system, of a real glass. And what would you expect of fluctuations in a system that has a quasi-symmetry? You would expect it to fluctuate a lot along the quasi-flat directions. So they did these plots, which would be the analog of plotting the radius here. And indeed, this is artist view, you find that fluctuations predominantly move along these lines. Okay. And here are their plots with real systems. You see the fluctuations are moving along these surfaces. So this is a story about glasses that tells you that for technical reasons, you throw a derivative, you think that it's a very reasonable thing to do, and you discover that the system is very soft towards changing the speed at which the film disperses. The film is always the same. Things happen together and in accordance. I always say, Ingrid Bergman climbs into the plane and Humphrey Bogart is at the same time crying, and this happens always at the same time. But the speed at which you're passing the film is extremely liable to be changed, either by fluctuations or by perturbations. These gentlemen also tried to do a sigma model. When you have something that is soft in a direction and hard in another, you would prefer to put all your physics in the soft things. So they attempted to write an action that only depended on the reparametrizations and nothing else. Okay, end of story of glasses. Turns out that this is a property of glasses. So it goes beyond the models in which it was discovered. Okay, story number 2. This is a different story. In the 90s, Sachtev, Subir Sachtev, Antoine Georges, Barcolero, wrote a model of fermions, in this case, in its present form, due to Kitaev, the fermions are Majorana fermions, but it doesn't matter at all, any fermions will do. This is just like before, but with different symmetries, random variables, and this is a quantum model. This doesn't have a glass transition. This is a quantum model, and it was introduced in those years with normal fermions, not with these, to study certain property of strange metals. Okay, so now you want to solve this model, and because it's quantum, you have to do a trace, and you need to introduce the Matsubara frequencies, the time, the imaginary time. So you're forced to do dynamics, you know this. When you do quantum, you cannot do things without time. And you write the equations, and maybe you remember, I don't want to go back, but this equation resembles a lot, and it's no surprise, the one I wrote for glasses. So you have only one correlation in this case. In the other case, we had 3, but it contains a derivative and some nasty integrals, very, very much like the one I wrote for glasses. And it's no mystery, it's more or less the same maths. And again, these people decided to throw this time derivative because this solution is a power law. It's not a glass at all, but it has a power law, so it becomes slow, and so this time derivative you think is negligible, but the problem you have again is that when you do this, you discover that your system acquires a reparametrization invariance exactly like before and for exactly the same reason. So a step further, this Kitaev recognized, I will tell you now, that these reparametrizations in this context have a very important meaning. So just I go up one step, and a sigma model of the reparametrization was written by these gentlemen, and it's over here. So you see that the logic is very close. Now let me tell you what all this means. They tell us, they meaning the string theorists, tell us, and don't ask me, that, you see, you start with a fermion model. You get your action in terms of G, just like before. And then you get your effective theory that only has the reparametrizations. They tell us that this is the exact metaphor for a quantum field theory going to a string theory going to gravity. So this theory of the cheap reparametrizations of time is, they tell us, a toy model of gravity. And it is a toy model of how gravity emerges from a quantum theory. So when you see this, you cannot help being very surprised. Before we were saying that we followed basically the same steps for glasses, classical glasses, interacting with a heat bath, and we decided that they respond basically by changing the speed at which they evolve, by reparametrizing, deforming their time. And here they tell us that exactly the same thing happens for exactly the same technical reasons, but the theory of these changes is the analog of how gravity emerges from quantum physics, from a quantum model. This part, I can only take their word for it, but we can believe that the metaphor is good. The difference is that instead of having to discuss very, very high-level models, to this model, you can ask the questions you want because it's a solvable, simple model. Okay, so, yeah, stop me. Exactly, this one. So the reparametrizations, as I say, were very cheap, but not completely for free. The small cost they have is written here. It's exactly analogous to saying the angle rotations are not exactly for free, but they're very cheap. So now I write a theory only of the energy cost of an angle, of moving, and I completely neglect the radius. So when you say that you're dropping the derivative and neglecting everything and your reparametrization invariance, the cost is zero of changing the film. But you know that there is a tiny cost because somehow a system chooses a reparametrization. The energy of the cost of changing the reparametrization is written here. It's a bit like when one does hydrodynamics, no? Where all the sources of energy end up by disappearing and you have the energies of the zero modes or almost zero modes. So, yeah?
So can you explain exactly what you mean here by dynamic heterogeneities in practice? Like, how do you introduce
I didn't
them
use the
those?
word though, but yes.
Like
I don't think I used the word dynamic heterogeneities, but
it's
yes, look at here. When these people said, okay, I have soft degrees of freedom, which is the time reparametrization, and hard, which is everything else. Okay, so then if I do a plot like this, which is reparametrization invariance, I would expect that fluctuations live along the times at which I look at this curve, so they live along this line. But this means that, for example, in a real glass, in real life, some places are going to be a bit faster than others, and these are the dynamic heterogeneity. Because it is almost for free to change the speed of a film, you can expect that the ages, how much the film has evolved, can change in space or from one realization to the other. So it has obviously no interpretation of gravity. While in this case, for reasons of their theory, the interpretation of these same degrees of freedom is that of gravity.
in practice, do these dynamic heterogeneities just happen spontaneously in a glass?
Happen spontaneously, or you can make them. For example, take a glass and, like I said about the ruler, and deform it, and a glass which behaves as 30 days old may rejuvenate to a glass that is evolving as if it were 2 days old. So its slow degrees of freedom become much faster. So you can have a dramatic effect if you know where to apply your. Okay, and I didn't mention this before, but this theory, when you look at the spectrum, you can put it in, diagonalize it. SYK model happens to have zero temperature entropy, so a lot of states that have very close to the lowest energy. And these are, they tell us again, the black hole. Of course, it's again metaphorical, but this is, they tell us, the analog of a black hole with many, many states, an exponential number. And if you want to do the theory of this, given that it's the theory of the lowest eigenvalues, it is encoded here because this is the theory of the lowest energies. So gravity, black hole, so this is their connection. So this SYK model is fantastic because if you believe it is a metaphor, this you have to have all their intuition to do, but once you believed it, you can ask the model lots of questions that you normally would have. Yeah. You will see it. Okay, you can ask the questions you want to the model will answer. So now we want to make a bridge because these, although the technical steps seem connected, how can we connect the two things better? Of course, we are not going to get a theory of gravity inside a glass, but how can we make these two things be together? So notice, I will establish that now, but I will start with classical relaxational glass dynamics. One thing would be, but I want to go to SYK that is quantum, so I quantize them. I am not going to do that. The glasses I will consider can be classical or quantum, and I will keep them classical. But my connection will be, as you see, a bit twisted. It's not going to involve quantizing the glass. You see now what I will do. So the evolution operator, remember that we had this Langevin equation that defined our glass. As you know, from a Langevin equation, you derive a Fokker-Planck equation which describes the evolution of probability associated with this potential. Okay, this is normal, and here is the glass energy in V. And I think most of you know that when you have a Fokker-Planck equation operator, you can take it to a Hermitian form. And when you do this, the operator you get is this one. And if you look at it, you see it resembles a lot a Schrödinger problem. It has a second derivative. This temperature, the stochastic temperature, is playing a role very close to h bar in a quantum system. And the potential is not the original potential, but it's this effective potential. So the classical problem of your glass or whatever you had interacting with a bath is now a problem of evolution, which has in it an evolution operator which, by a simple change of basis, becomes something that resembles a lot a quantum operator. So now I'm going to take this operator and I'm going to tell you that this is the quantum operator I have just invented, okay? And we will see that this quote-unquote quantum-like operator has some properties that are very close to the ones of SYK. And this will explain a posteriori why we are getting the same kind of things. Is it? Stop me, I have time. It doesn't have an I, and my time is Euclidean, you're right. Because by birth, when you're doing a stochastic process, your time is Euclidean. So it doesn't have an I. I can, if I want, add an I later, but then I lose a bit the interpretation. Okay, so something that perhaps you know, and if you don't know, it's quite natural. If you have a stochastic problem that has three valleys, let's say the temperature is very low, and you want to discuss, you have three metastable states, 1, 2, 3. And you want to see what the spectrum of this operator looks like. One can show, and it's a very interesting thing, that you get three states, eigenstates of this operator that are basically the ones I pictured here. They are concentrated along the minima of the original stochastic problem. You understand why? Because the zero is the stationary state of the system. And the almost stationary states, meaning the metastable states that live very long, naturally have a very low eigenvalue. So there is a connection between metastability and the spectrum of the Fokker-Planck operator. This is completely general. Now, translate this to the glass. The glass has an exponential number of minima, like in this picture. Below a certain threshold level, you have many minima, exponentially with the size. So now, the same correspondence I applied before, for each one of these metastable states, and there are now many, you have an eigen function of the Fokker-Planck operator that is very close to zero. In fact, its eigenvalue is 1 over the lifetime of the metastable states. And since all of these metastable states in a glass model are completely stable, these levels are essentially degenerate with the lowest, almost degenerate. So we now see that in the operator of evolution of any glass, not only the one, you will have an accumulation of eigenvalues, eigenstates, near zero, that play, and these correspond to the metastable states, which is what makes a glass a glass. And they are playing the same role of the black hole, quote unquote, in SYK model. So the softness of reparametrizations, which is the theory of these guys in SYK, is the softness of reparametrization here, very naturally corresponds to these low states, which indeed correspond to the part where the dynamics is slow, glassy, metastable. So this is the way to make a technical bridge between the two subjects. And you can play a bit more. You can change your stochastic temperature of your original system. It will have a glass point transition. And then the quantum temperature is this one, and you get a quantum phase transition, which is very much like a quantum phase transition of any kind.
Can I ask a quick question?
Yeah, where?
So about that glass spectrum that you just showed, so those metastable states are like the analog of the zero temperature entropy, right?
Yes, the zero temperature entropy is exactly the number of metastable states that live forever, because whose time diverges with them.
And would you say that in a glass, the primary contribution to slow glassy relaxation as opposed to fast relaxation would be these metastable states?
Well, to be more precise, when you're doing glassy dynamics, you're moving in this threshold level, which is where most of the states live, but they are the ones that, so this one lives much more, but there are a few of those, and you have more, until you get to a level where all the metastable states become unstable above that. And you are moving right above this threshold where your states are the most, but they are beginning to be unstable. So if you want glassy dynamics in these models, is like kind of self-organized criticality in that region. You are just at the moment where you have many states which are just beginning to have an infinite lifetime. So by far in this curve, because this is a log, almost all of them are here, almost all of them. And those are the ones that matter.
Okay, but would you then say that the slowest aspects of glassy relaxation, they would still be dominated by the metastable states? Right?
Yes, the slowest of the slowest, yes, and they are these. But in your life as an experimentalist, you will never get there. Okay. You will be wandering in a kind of labyrinth between not quite metastable states where you're wasting all your time. Okay, and in a more complicated system...
Jorge, can I just ask a very quick question? I got confused about the two temperatures that you just showed us. So one is the statistical temperature, which is essentially the temperature of your glass, right? The thermodynamic temperature. The other one came from the Fokker-Planck equation, but which physical scale is it related to?
Okay. So the one that came from the Fokker-Planck equation is the one of the bath. That one is the one of the bath because it's the one that enters the Fokker. The other one, you decide. The other one is the temperature you use for if you want to write a partition function with these states.
So related to the density of states of yours.
It's the density of states, exactly. So it has no interpretation in the glass problem. This is why I insist a lot. Yeah, I'm almost done.
Can I just?
Yes.
Yeah.
Oh, you're here.
Yeah. So what you're describing, the dynamics along the saddle directions. That doesn't correspond to the lifetimes which are giving you that piling up at the bottom.
Yeah, these are beginning to pile up. So if you have one saddle direction that allows you to escape, your time is not infinite, but very long. So you're beginning to pile up at the bottom. And then, so gradually, as you consider more and more piled up difficult situations to come out, you're closer and closer to this piling up.
Another yes or no question. So when you look at these mixed p-spin models, does that scenario hold?
Yes, with a lot of provisos. But one thing that is true is that you will have this, because you do have a lot of, but it's not as simple as saying I have a threshold and no. So I think that I'm done. Very quick, so this is just an advertisement. So people in the community of SYK are doing a lot of coupling together two systems. And with a very small coupling, these two black holes couple and make a wormhole. If you couple two glasses very lightly, this is something that has been done a lot in the glass world, it's like doing dynamics, two couples together, but with a very small coupling. And it means that you're exploring the states together. And this has interpretations and has been done in coupling. So things that are common are appearing in both literatures. So I wanted just to say that. Thank you very much.
So, so for the spectrum, you said like the fact that you have this exponential number of metastable states, they somehow map to the like a near degeneracy, which is also exponential.
The same number, actually.
Is that obvious, or that's?
No, it's not. So in general, this theory, the theory of metastability together with eigenstates of the evolution operator was developed by many people, but I can think of Gaveau-Schulman in a physicsy way, and Bouvier and others in a math way. It's very nice and very easy, but it's not very well known. When you read it, it takes an afternoon to understand how it goes, but you need to sit down an afternoon.
It's a rigorous statement. It's a rigorous statement, is it?
Oh, it goes to awfully rigorous if you want. But if you want a cheap version, we wrote an introduction with Giulio Biroli with the facts, the bare facts. If you want it a bit more serious and with everything, Gaveau and Schulman is okay.
So back to that zero temperature entropy thing, I just wanted to point out some kind of connection. So in glasses, they are the slowest modes, right? And in the context of SYK, we were looking at some relaxation processes in some sense. And it turned out that the zero temperature entropy is actually responsible for making that relaxation very slow, compared to what you'd expect. And previously, I wasn't thinking of that as glassy behavior, but do you think it would be fair to call it that?
Yes, I'm not, SYK is not the Fokker-Planck of somebody, as far as I can tell. But yes, when you say you were using that, you were doing real time. Yeah. So now imagine that I get this one. This one was born imaginary time because it comes from a Fokker-Planck. But I decide, contrary to any good sense, to make an evolution with an eye with this. I don't know to what it corresponds. And I do the calculation you're pointing out. I will get slow dynamics, which is obviously in some way related to the original glassiness. Not directly because it doesn't have a direct meaning, but so yes, but I am interested in these kind of connections which have not been worked out. So maybe we can talk later.
Yeah. So a related question actually. So this Fokker-Planck Hamiltonian, if you write it, I mean, how does it look? And if you sort of look at a quantum model, like, will it have?
Awful.
It looks awful.
Awful. But if you do a Glauber one, this is what we are trying to do now. You can do the same game with a Glauber. Glauber is a little bit nicer because you have spins, and so it looks like a nasty but still readable spin Hamiltonian.
So this picture that you show, you can actually calculate the spectrum of this Fokker-Planck equation?
Yes, to the extent that I know the statistics of the saddle points. This has been worked out ad nauseam in dozens of papers. So we know rather well how the states are organized.
So the complexity will be like the zero temperature entropy?
Yes, exactly. The complexity, and then, yeah, exactly. Everything you can say about complexity plus to know where they are, you can say about, yeah.
Other questions? So if not, let's thank Jorge for a very interesting